Okay.
Evet hocam, söz sizde Sedat hocam, buyurun.
Okay, welcome Zafer.
Hello, sir. Well, thank you.
We are quite pleased to see you here.
Thank you very much, sir.
After the first assessment, the jury decided that you can defend your thesis. Okay.
Thank you very much, sir.
So now the stage is yours.
Okay.
First, you will start to present your thesis.
Okay.
Meanwhile, we may ask some questions.
Okay.
By interrupting you. So this is how we will continue. Okay.
Okay. I would like to request Mr. Recep Güneş to allow me to share screens because I am not able to share the screen.
Okay. Ha, okay.
Recep, diğer katılımcılar dışarıda mı kaldı? Onlar katılamadı.
Hocam hepsini de kabul ettim ben.
Tamam.
Numan, you can share your screen. Okay.
Okay, sir. Can you see the screen now? I can start?
Yes, we can.
Yes, it is there.
Okay, so I have divided the whole presentation into 3 parts. From time to time, you will see me tilting towards left because I am presenting on the left monitor. So don't be confused why I'm looking on the left side. I have divided my presentation into 3 parts. First is introduction, objectives, and then the material methods, and then results and discussion. So our topic is microstructural and mechanical characterization of ceramic wires, which are reinforced in such a way that the phases inside the wires, we can control their shape and their fraction. And the second part is that we have made bulk materials by combining these ceramic wires. So this is the heading. And the presentation and the manufacturing method, the manufacturing approach which we have used is a novel approach. So this is the heading we seen appropriate. So the first part is introduction and the objectives. The presentation flow is in such a way. Let me make it full screen. I will introduce the topic briefly, and then I will give you a little research background and the reason why we use this study to do the research about objectives of the study and how we have planned the study and the manufacturing and how exactly we have done the manufacturing. So these are why and hows of this study. And then there are different methods in which we have characterized the material which we have manufactured. So the overall presentation flow is going to revolve around these headings. So in a nutshell, we have manufactured metal matrix composite wires. The materials which we have used is iron and B4C, bore carbide in the powder form, steel tubes, and eventually we have managed to synthesize iron boride phases in the material. This study is a new production approach for metal strengthening, and we have managed to synthesize ceramic phases at a micro scale. And for that, we have used boriding treatment, cold working, plastic deformation, and a predetermined ratios of the mixtures have been used by analyzing the FEBC system phase diagrams. The manufacturing, microstructural, and mechanical characterization has been used. Shape and fraction of the ceramic phases is controllable due to the approach which we have used in the manufacturing. And image analysis, metallography, tensile testing, and bending tests have been used. Eventually, the fractography have been used to check how the material has fractured after using these mechanical loadings. So what is manufactured? Metal matrix composite wires. The wires are monofilament wires in which the sheath of the material is used as iron and Fe2B phases as reinforcement in the wires. And another thing which is, and the second part of the study, what is manufactured is wire reinforced composites. Whatever wires we have produced here, we have combined them and made bulk material with that. So that is what has been manufactured. I will very briefly tell you about the metal matrix composite wires. If we can divide the metal matrix composite wires, we can divide them according to their properties. We have seen in the industrially active wires, which are high strength wires, high conductivity wires, high strength and high conductivity wires all together. The high strength wires are 4 millimeter to 12 millimeter wires, which are made of high carbon steel. We have seen them in the fences outside of the buildings for security regions. And then medium carbon steel wires are also available in the industry, and they are used like this. These are high strength wires. No other functionality is expected from them other than yielding and some ductility, and also as well as strength. Then the second part is the second type of wires which we have seen in the metal matrix composite wires are high strength and high conductivity wires. Me and my respected supervisor, Dr. Fahmi Nair, we wrote this paper, which is basically a review paper on the high strength and high conductivity wires, while I was doing the research for this study, for my thesis. So in this paper, we have shown how the composite wires are manufactured, what type of metal matrices are used, what type of strengthening mechanisms are used, what type of materials they use, and what type of methods they use to produce them. The most famous method for making composite wires is plastically deforming them. So what they do is they select a sheet of a metal, and then they put a strengthening element inside the sheet, and that material in a monofilament state is subjected to various plastic deformation techniques. You can bundle them, you can deform them, you can cold roll them, you can heat treat them, whatever you want, but the main purpose is to plastically deform them from this size. This is about from 8 to 12 millimeter, and then it comes into a maybe 2 millimeter wire size. After passing through this series of cold rolling and heat treatments, the wire is the tensile strength of wire is extremely high, and then you can use these wires. But because the material which is used in this approach is selected in such a way that you want an exceptional functionality from them, copper is high conductive, so they are also high conductivity, high tensile strength wires. Here is another example. Copper is filled with graphite powder. Again, passed through a series of plastic deformation, and eventually wire is in such a diameter. Plastically deformed, deformation processed composite wire. Here is another example. Copper and niobium is combined, again passed through a series of plastic deformation techniques, and eventually you get a composite wire. Now, the fact that you have used bundling and deformation, and you have the ability to use the wires at a predetermined place, you also have an authority and a control over the cross-sectional profile microstructure of the material. This is a monofilament wire, copper and niobium, and this is a multi-filament metal matrix composite wire strengthened by the secondary elements present inside. I have compiled 3-4 examples. Okay, here I have this table belongs to my thesis. I have selected this to show how different types of composite wires are used and what type of technologies they use. For example, mostly we see powder in tube, but there are also available rod in tube combinations and other combinations. Eventual size of the wire is in this range: 0.7, 2.5 millimeter, 1.2 millimeter, 2.10 millimeter, and 1 millimeter. These are the number of filaments which are produced. How do we know the number of these filaments? Because we have used plastic deformation, and each rolling pass which we have used, it was in our control. So we know at which monofilament we started, and eventually how many filaments have we established inside. So these are the range of diameters of composite wires after the deformation. And these are the starting diameters, 8 to 7. These are some fields in which these wires are used, composite wires. They are used in...
1 second, please. Could you go back to the last page?
Yes, sir.
You said it is related to your thesis, or this is something you have done.
This
What
is
does it
already, no, this is not, this is the background of my study.
That's it. Okay, so this is information from literature.
Exactly.
Okay.
What the composite wires are, which diameters they have used.
I wasn't sure about why I said, okay, so when you said it belongs to my thesis, I thought you did it. Okay, of course
No,
not.
we did not do this. This is background.
Okay, from the literature. Mhm.
Yes, actually a published paper also.
Okay.
These are the applications, long pulse, high field. Why? Because they are conductive, and high field electromagnets, because during the making of electromagnetic fields, you need high strength wires because of Lorentz forces. High voltage electric transmission wire cables, aluminum, because it is light and it is also conductive. We use there. Bulk materials at nuclear sites. Bulk materials at nuclear sites are used because, again, depending upon the type of strengthening element, if it performs well and if it does not swell at the nuclear sites, you can use it there. Antibacterial implants, copper niobium wires are used as antibacterial implants because they are compatible with the human tissue. And diamond wires are the wires which are used for cutting slabs, ceramic materials, because they are high strength and high conductivity. You can use it as the cutting wires, and they are famous diamond wires because diamonds are impregnated on the sides of the wires, so you can use them for cutting the slabs. Okay, now after that, I'm coming to my thesis. If based on the paper which we have published, I have seen that many people have worked on the composite wires. If you see the literature, there are a lot of studies in which they have reported the microstructure and other many aspects of the composite wires, but very little they have made wire reinforced bulks. They complete the manufacturing at the wire level and then nothing else, because their eventual purpose is to make wires. Very few studies have used wires as a reinforcement element in wire reinforced composites. Here is copper, magnesium, and aluminum are the dispersed filament reinforced wires. I have already given you the background about this. Here are the functional wires, which are used as lightweight structural components. Applications and type of materials are reported, but we go there, we studied this, we made a wire about this, but then we proceeded to functional reinforced composites. Functional wire reinforced composites, to be exact. How are the functional wire reinforced composites are made? The most famous technique is squeeze casting. You take a wire, you clean them, you stack them, you put a metal melt on it, and then eventually you machine to the resultant final product. And that is a wire reinforced metal matrix composite. This technique is industrially active, but it is an old technique. Here's another technique which is also used for wire reinforced composites. You take foils and you put the reinforcement between the foils, you compress them, you put them at elevated temperature, and then you wait there. Eventually, at these areas of the foils, temperature assisted bonding occurs, and eventually this structure is acquired. This structure is similar to this one, but these two techniques are the ones which I have came across, in which some studies are reported, have reported the manufacturing of wire reinforced composites. Here is
Zafer.
Yes, sir.
Go back. One page back. Yes. Here, the thickness of the foil is more or less the same with the wire. So would you call them plates or foils? These ones.
We can call them plates, not foils.
Yes. Okay.
We must call them plates. You are right. We must call them plates.
Yeah.
Foil is something which is used to assist only the bonding,
yes,
not serving as a matrix.
Yeah.
If you actually desire to make a matrix, we must not call them foils. We must call them plates.
It could be better, probably. Yes. Go on.
Yes. Yes. But if you look at this image, you see that the thickness of the foil is not actually foil. This is a matrix form. but because the literaturally active term used for that is foil, so I have used foil. But actually, I was also thinking that it is not a foil.
Okay.
I agree with you. So here is an example from the literature in which wires are used as reinforcement, and here the bonding has partially occurred, not completely, and this titanium is working as a matrix. So why is it important for us to, in the heading, you see that distribution, shape, and fraction of the ceramic phases is controlled in the monofilament wires we have manufactured. Why is it important to control the morphology of iron boride phases? I will try to answer these two questions. So the current ceramic particle reinforced wires which are produced in industry right now, they use the mechanical approach with that. What they do is they use the extrusion and drying. Before extrusion and drying, they mix the powder forms of ceramic particles with the metals, and they are subjected to extrusion, drying, other techniques. For example, powder mixing by ball milling and other techniques are also used. And then they are hot pressed. A series of treatments which I have shown you in the previous slides, and then eventually the ceramic particle reinforced composites are produced. The ceramic particles work as a strengthening element of the composites, and a ceramic reinforced composites are produced that way. This is a mechanical approach. They use physical or mechanical methods, these ones, to distribute the ceramic particles in the metal matrix. But because the ceramic particles really hard, they are not allowed to, these methods only help in distributing, and the most work they do is on the matrix because they plastically deform the matrix, and they cannot do it with the ceramic particles. So they do not have a good control on the geometry of the ceramic particles inside. We propose a chemical approach. In a chemical approach, what we can do is that you again use the powder metallurgy, but you use them intentionally in such a way that you can have a thermodynamical interaction between the particles at elevated temperature. If you do that, then maybe there is a chance of changing the morphology and the size and also the distribution of the ceramic phases in the metal. So metal matrix is reinforced by the ceramic phases instead of the ceramic particles. As I told you that we need to have some knowledge about the interactions of the used powder particles at elevated temperature. You must use binary ternary phase diagrams to understand what type of phases are going to be produced. Powder metallurgy, of course, is necessary. I will show you why. And hot pressing and consolidation at elevated temperature. So this chemical approach can be used to make also ceramic phases reinforced metal matrix composites. Here is another paper. This is an unpublished table from my thesis in which I have shown the studies are very rare, but I have been able to find maybe 10 or 12 of them, in which irons have been reinforced by the B4C particles, and titanium has been reinforced by the B4C particles. Aluminum has been reinforced by calcium, and these types of materials, these type of studies, they have used powder metallurgy, as I told you, elevated temperature treatments to in situ synthesize these ceramic phases inside the material. But none of them have used post-compaction after compacting these powder forms techniques, except aluminum, in which they have used extrusion, but they have not produced bulk materials. This study belongs to composite wires. This is my study in which I have used cold rolling after the compaction, and I have also used elevated temperature sintering. And my in situ synthesized phase is iron boride. Here is an example of the microstructure in which titanium carbide is reinforced by the in situ synthesized secondary phases. Powder form without any phase, and powder after the heat treatment is strengthened by the secondary phases. Here is another example in which titanium is in situ reinforced by these secondary phases. So metal reinforced by ceramic phases, chemical approach. Okay, this is totally related to my study because they have used iron boride phases, iron boride, low iron boride and high iron boride phases, and they have used iron as host particles for the strengthening of iron particles. But before going to that, we need to understand what exactly is going on here. Boriding is a surface treatment which you all might have heard, in which the boron particles are impregnated. Actually, they are diffused into the iron lattice and surfaces of the steel materials. Steel host are hardened, and they are used in wear applications, mostly in wear and high oxidation applications. And they give the corrosion resistance to material. What happens is the formation of hard iron boride phases occurs on the surface of the steels. We have used the same phases, not as a surface enhancing phases, but as an in situ strengthening. So our approach might look like that the same physical and chemical phenomenon is happening, but it is different because we are using it as an in situ synthesis of iron boride phases, which will eventually strengthen the matrix. Here is very old but very important studies from the literature in which iron particles have been in situ synthesized by the iron boride phases. This approach is similar to ours, but again, no control on the morphology, no control on the formation of these secondary phases. Here is another example. This is a Turkish guy who used similar approach, not similar, but he individually borided these iron host particles, and he was managed to get these ceramic phases on the surface of on the surface of iron particles. Here is another example in which in situ synthesized iron boride phases are used, but because they used a very high temperature, a liquid phase was formed on the surface, so they were not able to control the composition of these phases. But this is also an example from the literature in which the iron particles have been borided. Last night when I was checking the literature, I just came across that on 31st of August 2022, Metals, which is a very prestigious journal in our field, they have opened an option of ceramic reinforced metal matrix nanocomposites. And when I was studying the details, it was shown if you have a new processing approach, a different processing approach, any chemical approach is also welcome in which metal matrix is strengthened at nanoscale. So objectives of this study is Fe matrix, Fe2B phase reinforced monofilament wires manufacturing, morphology, shape, and distribution of the fraction of the iron boride phases is controlled. And then ceramic wire reinforced bulks are produced in which Fe matrix is reinforced by the wires at a macroscopic level, and wires are further reinforced by the iron boride phases. This is the type of anticipated material which we are expecting. Atomic level, iron boride phases inside the core of a wire. Core is going into the steel, and a composite wire is produced. And then these wires are combined in the bulk level, and this is a ceramic wire reinforced metal matrix bulk, side view and a cross-sectional view. So microstructural characterization is a typical microstructural characterization. I have studied the core deformation behavior of the powder particles before phase synthesis, and after phase synthesis, I have studied the influence of B4C content in the boriding of Fe particles. And here also I have reported the microstructure of wire reinforced bulks. Because I'm going to show you all of them individually, I don't want to waste any time here. The mechanical characterization is done by the tensile behavior of Fe2B reinforced composite wires, and ultimate tensile strength of the wires is also reported, and the hardness of the sheath and the cores of wires is reported. All these studies are mechanical studies which are at the wire level, and then these studies are at the bulk level. We have used 3-point bending tests. Interlayer shear strength of the wire reinforced bulks is reported, and hardness of various regions in the wire reinforced bulks is also reported. So these are mechanical characterization objectives of this study. Why? I have told you that we have been able to control the morphology of iron boride phases at the wire level. But why is it important to control the morphology of Fe2B phases? And why is it important to make wire reinforced composites instead of surface boriding? I will try to answer them now. In 2021 November, this paper is published while I was studying, while I was trying to find a way to control the morphology and orientation of Fe2B phases. This study has reported the influence of the morphology of the Fe2B phases on the erosion wear behavior of, again, iron boride alloy. Here are some old studies in which different methods have been used. For example, different methods have been used to control the morphology of iron boride phases, effect of orientation, influence of iron boride phases on corrosion behavior, and then different ways to control the morphology and the size microstructure of iron boride alloys. So this topic is industrially and in the literature is a new topic indeed. All of these studies, they have used casting, and they have used elevated temperatures to do the same thing. I have managed to do the same thing without involving liquid phases and without using an elevated temperature. And here is the reason. One might ask, why going through all this trouble and not just surface boriding the material? The surface boriding of the steel is used only for corrosion and wear resistance, aggressive environments. And mostly whenever you have a steel, because you have a lot of wanted and unwanted elements in the steel, whenever you apply the surface boriding on the steel, there is this softer sublayer which is formed under the borided element. In such a case, in this approach, we don't believe something like this will happen. These are my wires, and this as a whole is a wire reinforced composite. This will eventually fail when the wear of above top surface is gone. This will allow a continuous supply of iron boride phases during wear applications. And this material is not only for the wear applications, this is also used as a wire strengthening, as a composite metal matrix strengthening. Okay, here is the proof.
Zafer?
Yes, sir.
You are giving some examples, that's okay. But in a precise words, could you tell us what was your aim? Okay, when you manufacture such a material, what would be the end use? Okay.
Okay, sir.
It could be hard, okay, soft, or whatever it is, a hard material, soft material, or a material which is resistant to corrosion, resistive to corrosion, but at the same time strong, so it will be used in such a industrial field. What was your aim?
Well, first of all, my aim was to somehow, because they have been using, as I showed you here, they have been using these different methods to control the morphology of iron borides. And the main purpose of them using the iron borides, they were actually trying to control the corrosion behavior, and also they were trying to make a material which is corrosion and wear resistant, using a quite difficult manufacturing approach. My main focus was to use an easier and much least complex manufacturing approach, but eventually our applications also, because the phases which are produced are very hard and tough at the same time, they are eventually most suitable for the wear and tribological applications.
Okay, let's say I am a manufacturer, okay?
Yes,
I want
sir.
to invest money, so advise me. Where shall I use this material?
Well, I was discussing this with my supervisor. He also told me that.
Of course, this is the core question.
Yes, core question. Because these wires are produced as a strengthening element, they can be used anywhere where you want a wear-resistant material in a tribological applications. I believe so.
Okay, military equipments.
Military equipments, because the metal matrix is conductive and lightweight.
Yes.
Also in the magnetic applications, because we have used steel as a sheath, and it is a lightweight material. And also in the previous study, Dr. Mustafa has studied the impact behavior of these phases. So they can be used in military applications. They can be used in the sleeves of the pistons. We have discussed this. Wherever you have wherever you require hardness and toughness at the same time,
okay,
you can use this strengthening element wires.
Turkey is now using high-speed trains.
High-speed trains,
so,
of course.
Can I use this material there?
You can use this material if your wires at that specific structural component requires high hardness and at the same time conductivity. Of course, we can use this.
Okay, thank you. By the way, it has been 35 minutes.
I will go very quick. I will go very quick after this.
Go to your concentrate on your own work, okay, Zafer?
Okay, okay. How much time do I have?
Totally about 2 hours we are planning, so you have about 1.5 hours at most.
I will finish in before that.
Okay, that's good news. Go on.
Here is some studies which have attempted a different approach to control the subsurface of borided steels. Here is a formation of a soft layer which is reported in the steels. Something like this, a softer sublayer. In such a material, something like that will not occur.
It will be more uniform. Your material will be more uniform. Is that correct?
Yes, it will be more uniform, and also because and also because I am not using a steel which has many elements inside, and then I need to take care of each element differently. I have used low carbon steel, so something like that is not going to occur in this proposed material.
Then it could be cheaper, maybe. Is it possible?
Of course, yes, it is cheaper.
So just put them forward, okay? The positive sides.
Yes, okay. The manufacturing of wire reinforced composite wires is very simple. Tube filling, cold rolling, and phase synthesis in a nutshell. Here is a schematic of tube filling. And this table is going to be very useful when we are going to investigate the phase interactions of these materials at elevated temperature. So out of these powder mixtures, I have used these formulas to measure the elemental composition with the weight percentage for these powder mixture ratios which we have used. These are the type of wires I have manufactured. Outer diameter 8 millimeter, inner diameter 6 millimeter, 5, 10, and 15 volume percent reinforcement of B4C particles. And these are the pre-sinter and post-sinter state wires.
Zafer,
yes,
sorry
sir.
for interrupting, but sometimes I need to ask.
Sir, the more you ask, the more I will be directed in the right direction. Thank you.
These percentages, are they from literature or from experience? 5,
no,
10?
These are from a very comprehensive analysis I have provided. I will show you in the next slides.
Okay.
They are not random.
I didn't say, are they just from literature or from past works experience?
These percentages are provided because I want to make a phase of only a single phase, low boride phases, and these are after an analysis we have done on the ternary and binary phase diagrams. Okay. After studying that, we have used these ones. These ratios correspond to these weight percentages, and these weight percentages correspond to the phase diagram, the type of phases we want to acquire.
Yes.
After filling the tubes, here they are subjected to this cold rolling device from 8 millimeter to about 1 millimeter. The cold roll wires are reach from this state to this state. These are the dimensions of the material, and they are capped with aluminum so that the powder does not remove whenever we whenever we subject them to cold rolling, plastic deformation. This is the cross section of the wires. At this state, we have only powder mixtures inside the core, and outside we have steel sheets. And you go down as the deformation level increases, and these are the wires from the side view. Another image of the wires so that you can have an idea of the dimensions. This is the schematic representation of the wire reinforcement, wire reinforced composite wires manufacturing, tube filling, compaction, cold rolling, and this boriding treatment. 1100.
How long are these wires? How many meters did you manage to draw?
We started with 1.2, we started with 120 millimeter, and they reached to sometimes 2 millimeter, 2.5 millimeter, sorry, 2 meter and 2.5 meters.
Did you experience breaking failures?
Only when this sheet is so short, anytime you go through rolling, it will fracture from here.
Okay.
Yes. But if you see, they are bendable, and being bendable is a good thing indeed, because
there is flexibility.
What we are expecting from the materials is that this is a powder mixture in the non-deformed state, and this is the powder mixture arrangement after the deformation. Before, C particles being ceramic and hard are not going to experience any deformation, but the iron particles, the white ones, they are going to be elongated after the cold rolling. This is something we are anticipating right now.
Of course, it is expected.
These are the things which we have studied. Influence of deformation levels on the sheath and the core. Influence of the deformation on the powder particles. Influence of the reinforcement ratios 5, 10, 15 on the powder, on the borided region. The reinforcement ratios influence on the borided region, and influence of deformation on the boriding treatment. These 4 questions we have asked after the manufacturing. So, summary: 8 millimeter wires filled with 5, 10, and 15 volume %. You go down, increase the deformation level. You have these type of wires, and then for each set of reinforcement ratios, you have these much wires with you. Then these wires in the pre-phase synthesis wires, because there is no heat treatment applied on them yet, they are subjected to in situ boriding, and then you get another set of wires, which is believed to have iron boride phases inside them, and then you have all these parameters which you need to investigate about these wires. Influence of deformation level, influence of increasing reinforcement ratios in the pre-phase, in the pre-sinter state, and then again information of influence of deformation levels on the borided regions, and influence of increasing reinforcement ratios on the borided regions in the post-sinter state. Here is a graphical representation of my work. Tube filling, manufacturing. This is the core microstructure before the synthesis of iron boride phases. Here is the core microstructure after the synthesis of iron boride phases. This bulge structure you see in the microstructure, it is iron boride phases. And this background you see, it is light background, that is iron matrix. So at this stage, we can say that we have managed to do something, but in detail, I will show you in the next slides. Microstructural analysis. This region is transverse to cold rolling. This is parallel to the cold rolling. Influence of all these deformations on the hardness, tensile testing, and fractography. The next is manufacturing of wire reinforced bulks. Again, very simple: tube filling, cold rolling, and phase synthesis and interwire diffusion bonding. 3 steps, not too complicated. And explained until this, and now I'm explaining this region. This is something we are expecting, putting the wires together, and eventually after the treatment, we expect a material like this. All these wires are expected to be bonded like this, and these are reinforcement. The sheets of the wires are going to serve as the matrix after the treatment. So what do we have? Option 1, tube filling, cold rolling, phase synthesis, and wire bonding. It is not as simple as that, because after the phase synthesis, the sheets of the wires are going to be oxidized, and you will have to clean them, go through a lot of machining, cleaning, chemical cleaning, maybe physically abrasing them before you can bond them together, which is not practical. So we use the second option. This is inevitable. You cannot escape from these two steps, because you have to have composite wires at 1 millimeter, 1.5 millimeter level. So we want in situ boriding in the cores of the wires and interwire hot diffusion bonding at the sheets of the wires at the same time. Only then it is going to be something practical. These are the schematics of bulk manufacturing. Already explained until this. 30 by 30 millimeter clean wires are stacked together, and then they are subjected to this heat treatment. And eventually we expect something like this. Diffusion of boron atoms from the B4C particles to iron, and synthesis of iron boride phases in the cores, and interwire hot diffusion bonding at the sheets. So again, this treatment is same as the old one.
Numan,
Increase the temperature. Yes, sir.
I have a question for you.
Yes, sir. Yes, sir.
What is your main purpose in obtaining the plates from wires? Why didn't produce it indirectly, the bulk material or plate?
I'm not.
What is the main purpose in obtaining the plates from wires?
Okay,
Why
sir.
Produce a plate indirectly.
Sir, as I told you, we want a material which is strengthened at the wire level, and also the wires are strengthened at the iron boride phases. With the iron boride phases, we want a material which is a soft because of the presence of steel, which is recrystallized after the treatment, and it will give the toughness to the material. And at the same time, we want the material to be hard because of the presence of iron boride phases. At this level, when they will be joined together and they will be put at 1100 degrees centigrade, it will make a softer material. At the same time, inside the cores, you will have iron boride phases, which will be very hard. So we are combining two different types of properties, contradicting properties in the same material. That is the main purpose of all this manufacturing here.
Okay, thank you.
Can I join the discussion, Zafer?
Yes, sir.
Maybe it will be difficult to diffuse the boron carbonates through the thickness if you use the bulk material.
Yes.
That is the main obstacle. Here,
exactly.
You can diffuse from the center towards the other sides, okay? But if you use a bulk material, you cannot diffuse.
Exactly.
Then you will get surface condition maybe.
Exactly. You explained it better than I do, because it will also form, eventually the boron diffusion will stop after a certain millimeter, after certain micrometers to the surface of steel. If you want to proceed to the more iron boride phases, you have to use an in situ approach. And the pressure is also increased eventually, and it reaches to 35 megapascal. But why 35 megapascal? Okay, here is the state of wires at different manufacturing levels. And these are the type of wires I have produced for the second generation for the bulk material. Now, because I have seen that the iron boride phases can be synthesized in this way, I should just expand the study. So I compared this with the reference material, steel 1.5 millimeter wire, no core, no reinforcement, nothing. So it is a 000 specimen. Then there is a core, but only iron particles. Then there is a core with 10, 15, and 20 volume% reinforcement ratios. Then the core diameter is increased, again 10, 15, 20. And then again the core diameter is increased, and 10, 15, and 20. So all these specimens are prepared again for seeing the influence of iron boride phases, again at the pre-sinter state and also the post-sinter state. And the B stands for the bulk material, S stands for the sintering after the sintering, and N stands for the non-sintered before the synthesis of iron boride phases in the wires. So I have three, because I want simultaneous iron boride formation, and also I want the interwire bonding. I need to take care of these three parameters. I will go one by one. Pressure, which is an important parameter. I need to know what type of pressure I should exert for the wires to be bonded. Temperature, nothing much I can do about that, because at least above 900 degrees centigrade is required for the in situ synthesis. And duration also, because diffusion of boron to the iron requires a lot of time. We must have enough time to ensure formation of iron boride phases. For the pressure, what we did that was hit and trial. Lower temperature, low pressure, increase the pressure to 35 megapascal, and eventually we saw that these wires are able to join at this level. In this place, you can see that there is no voids. At macroscopic level, you cannot see voids. So we decided that our treatment temperature should be 1100 and the pressure should be 35 megapascal. This parameter is defined to see the complete bonding. It is defined by the bonded length divided by the overall overall circumference of the wires. And this parameter reaches 1 at this value. So we used 1100 degrees centigrade and 35 megapascal. Okay, the next thing is, how are you going to make this phase synthesis if you don't know the type of mixtures ratios you should use? For that, we need to calculate the phase diagrams. I learned to use this software. It is called thermocalc. Maybe you have seen in the literature. It draws the phase diagrams for the compositions which you have used for the elements, and it uses this online database for calculating the phase diagrams. This is a boron and carbon phase diagram, nothing overwhelming here, even at 1600 degrees centigrade. These are the ratios which I have used. Even at 1600 degrees centigrade, nothing much is happening here because they are small atoms and they are covalently bonded. Here is a typical iron carbon diagram. We will be working at 1100 degrees centigrade. So I expect my material to be austenite, my phase to be austenite at that temperature. And here is an image of iron boron, which is again calculated for the compositions which I have used in this study. But because I am using three elements, I should find a way to introduce carbon into this phase diagram, or maybe I should find a way to introduce boron in FC phase diagram. For that, with the use of that software which I have just showed you, I was able to draw the ternary phase diagrams of the material. Now, after drawing the ternary phase diagrams, I need to know where am I working? Am I working here or here? But because I have already calculated the weight percentages of each element, it is very easier to know where I am going to work. This region belongs to the types of, this region belongs to the elemental ratio which I have used for the powder mixture preparation. The next step after that is go to literature and try to find what type of phases are formed at this region. So this data is acquired from the internet and also with the use of the software. I am going to work in this region. And here, this one is a magnified version of this phase diagram. So I expect a gamma and Fe2b phases to be produced at 1100 degrees centigrade. These ternary diagrams are the isotherms at 1100 degrees centigrade. If you go to 900 degrees centigrade or 850 degrees centigrade, you will have different type of phases. So this analysis is important if you really want to have a single phase material. But there comes a question, why do you want to have a single phase material? Well, that is something to do with the cracks which are formed on the borided surfaces. This paper is published 2 months ago. in which we have characterized the types of cracks which are formed on the boraided surfaces. This is not related to our study, so I will skip that. But while we were investigating the type of cracks, we came to realize that FEB phase and FE2B phase, they are not compatible, simply because they have different thermal expansion coefficients, and anytime you try to use them or they are cooled in an unwanted way, they are going to crack at the boundaries. So always the people who are working with the iron boraiding of the materials, they prefer to form a less brittle, a hard and tough, low iron boride phase instead of FEB. Here is another example. It's a Turkish person who studied this. He also reported cracks being formed on the FEB and FE2B phase. That is the reason we must ensure that you are expecting iron boride phases with the types of ratios you are using. That also explains the type of powder mixture ratios we have used, 5 to 20%. So tensile testing of all the compositions, all the structural configurations which I have shown, because the wires are 1 millimeter in diameter, it is very difficult to conduct a tensile test in such wires. You must have a comprehensive gripping system which can grip the wire, not strong enough to crush it at the grip level, but not weak enough to
release it.
Release it and to pass over it, and without transferring the stresses to the gauge length. Here you can see that my supervisor, Dr. Fahmi Nair, he managed to find this. This is his work. He managed to find these gripping systems when we use them, and we managed, after many hit and trials, to break the wires at the gauge lengths. Then we proceeded with the respective experiments. The short beam test after the wire reinforced composites are given here. They are cut from here, these two planes, and then they are subjected to short beam shear tests. This setup is also domestically made in our lab, and it allows to adjust the gauge length, the length of the material, spanning length of the material of the testing setup. So what did we investigate? Use different structural configurations and tensile behavior of the wires at wire level, and influence of different structural configurations on the bending behavior at the bulk level. These two things are investigated about the wire reinforced bulks, and then also reported the interlayer shear strength by the 3-point bending test. Last part of the presentation is results discussion and conclusion. This nomenclature I have already explained. I will explain with the next slide. These are the type of materials which we have produced: 2 reference materials, and then increasing diameters and increasing reinforcement ratios. These are the components of the wires. Outer component of the wire is known as wire sheath. Inner component is known as wire core. This direction is parallel to the rolling direction, and these 2 directions are the transverse directions. Parallel to rolling directions, you can see that these are iron particles. They are all elongated in the direction of the rolling, and these are transverse images. These iron particles are compressed. The first question was, how is the distribution of B4C particles going to influence the microstructure? The answer is that at lower reinforcement ratios, you don't see agglomeration, but at higher reinforcement ratios, you see these B4C particles, they are agglomerated at the interwire boundaries.
Is it too much, Zafer? Agglomeration?
Too much, but we have a solution for that. I will explain now.
Because they may cause problems if there are.
Of course, they will cause problems, but because they are subjected to cold rolling, they will eventually disappear.
Okay.
Here is the influence of deformation on the iron particles. These iron particles, these images are shown at same magnification level. So you see the scope of the microscope is same, but a higher number of particles are introduced inside the scope of material. This shows that these particles, they are compressed and plastically deformed.
What is the difference ABCD? What do they represent?
ABCD is increasing deformation levels.
Okay, okay.
Deformation level is increasing from the left side to right side.
Smaller
85,
diameters. Yes. Okay.
Yes.
Okay.
These images are taken from the wire cross section.
Mm-hmm.
But in order to see what is actually happening, we need to see the images from the longitudinal view. So again, increasing deformation level is shown, and the images are shown from the longitudinal view. Thanks to the cold rolling and the compressibility and how to say ductility of the iron particles, deformation levels caused plastic deformation, caused elongation of iron particles in this form.
Zafer,
Yes, sir.
I understand that the iron is elongated. Okay.
Yes.
What happens to the hard particles? Are they also elongated?
Of course
Are
not.
they
They are. Of course not. Of course not. All the hard particles, they are embedded inside
Yes.
the material.
Okay, they distributed all.
Exactly.
Along. Okay. Okay.
Exactly. I have a few pictures of the microstructure in which influence of agglomeration on the materials boriding is shown. I will show you at that time also. Mm-hmm. So we decided to see what happens to the iron particles when they are deformed. So we did a hardness analysis scan on the core of the material before the synthesis of wires. We see that increasing the deformation levels causes a slight increase in the hardness of iron particles, if you see here. And the average size of the iron particles is reduced like this. The micrometer square of each particle is reduced as the deformation level increases. This allows us to have a quantitatively explain how the size of the iron particle is reduced.
You mean is it the area?
Area of each particle.
Okay. They are circular, I would say. Are they?
No, not circles, different geometries.
Okay.
Mm-hmm. But you are right to ask, how did you measure the area of iron particles? So that is done using a computer program and using image analysis. What you do is you convert the microscopic images into high contrast image, and then you tell the program to draw the boundaries around each particle. And then each particle is individualized. For example, this is P20 and P24, and each particle individually is reported as a clustered image. And then using this scale, they report you the micrometer square area of each particle. But if you see the image, you see that some particles are really big and others are small. You must find a way, if you are actually claiming that I have done a quantitatively analysis of the particles.
Pardon. When you say particles, just name which particles? Probably iron particles.
Only the iron particles.
Huh.
I'm discussing only the iron particles because there is nothing I can do about the B4C particles. Mm-hmm. They are very hard and they have little influence on the B4C particles.
They don't change their shapes. Okay.
Yes.
Sizes.
Yes. So the iron particles are individualized using this methodology, and then at each particle is handled individually. The computer will draw an infinite number of lines, and then using these lines, he will report you the geometrical aspects of the material. For example, if I tell the computer program to measure the average diameter of each particle, what it will do is it will draw an infinite number of lines, add their lengths and divide them the number, and it will report me the average diameter of each particle. Average diameter of each particle will be measured like this. Then it will go to the next one, and in the image, it can give me a distribution of the iron particles. It will tell me how many particles have a diameter of 2 to 3 millimeter, and how many iron particles have a diameter of 10 to 15 millimeter, for example. Only then we can say, if I give you an average number of a diameter, if I give you an average diameter of this micrograph, it is not going to be a correct value. This methodology can also be used to measure the aspect ratio of each particle. What it will do is it will measure the longest length and divide with the shortest one, and it will tell you how the material's aspect ratio is increased. For example, this one has a larger aspect ratio. This one has a smaller aspect ratio. It can also give you the roundness of the material. What it will do is it will measure the diameters of all particles, and it will see which one is different from which one and how many micrometers. And then it will give you a measurement of the roundness. A circular particle is going to be reported with zero transition from the diameter, and it will be called a perfectly round particle. Here is the methodology which I use to measure the iron particle size. I tell the material to behave the white color as a foreground and black color as a background, and measure the size of the iron particle. And the rest is all on me, what I want to measure and what I want to do with this iron particle. I did this to all these particles at most deformation levels. And then I reported these iron particle sizes. And I also used that to measure the distribution of iron particles at different deformation levels and at different reinforcement ratios. N5, N10, and N15 show the influence of reinforcement ratios on the co-deformation behavior of the iron particles, going from the lower image to the upper image. You see increasing deformation levels. What we see is there is a fair distribution of iron particle sizes, but when you go to the higher deformation levels, the layer is shifted towards the left side.
Left, yes.
So it means that a large fraction of iron particles belongs to the smaller size iron particles. Okay, this is the ultimate deformation level which I have been able to achieve after the cold rolling. These are my 1 millimeter wires, in which you see that all the agglomeration which was occurred at N15 at the lower deformation levels have reduced to the higher deformation levels. They have been forced to be embedded in this direction like this. This condition is favorable for us because agglomeration is not desired. And the electron microscope images also reconfirmed that iron particles have not been agglomerated anymore thanks to the deformation level. But I can call this a microscope. I can call this a microscale work because iron particles of 2 millimeter thickness can also be witnessed. These are B4C particles, all of them, and these elongated particles are iron particles. This state of the particles is something which we desire. Here is a lower deformation level, agglomerated iron particles, a higher deformation level, no agglomerated iron particles here. But I can see that this iron particles is surrounded by iron boride particles. And this iron particle is surrounded by B4C particles. And this condition, this particle is going to be subjected to boriding from multiple directions. In our previous paper, we have shown the aspects of multidirectional boriding on the iron. And these regions are the ones which were in contact with the iron powder from two different directions. So there were iron borides formed. So we can believe that the iron borides will also form on the iron particles. They will overlap and there will be not seen any geometrical discontinuity on the iron particles after the boriding. So we are safe with this type of microstructure, I want to say. So these are the particles before boriding. In situ boriding has caused the formation of iron borides in such a way. You can see that the lower reinforcement ratios have caused a smaller iron boride phase synthesis. These darker regions are iron borides and the background is iron matrix. These are also iron boride phases, and this is also dense iron boride phase. it is very relieving to see that there are not seen any other phases. For example, if you have an iron boride and a high iron boride phase at the same time, you will clearly see the difference because of the tone. Because of the tone of the color after the etching. We see only a single color for iron borides and a background, we see iron matrix. And here is the sheath core interface. It is very continuous. These grains are ferrite and pearlite grains because the wires are subjected to elevated temperature and rearrangement of the grains occur there. They are coarse grains. And here is a region, inter-iron particle region, in which there was no B4C particle to serve as a boron host. So they don't have any iron boride phases formed here. But all other regions at which iron particles were in contact with the B4C particles, iron boride phases have formed. Here is a method which I have developed again using the image analysis and using the color coding to measure what type of percentage of a material is borided after using a particular ratio of the reinforcement of B4C particles. This is the methodology. I have already told it is used by the color coding, so I will not. I hope that you have already understood this. So this quantitative image shows that by using 5, 10, and 15 volume % of the reinforcement ratios, you can have this percentage of the material to be borided based on these images. Now, the next step is to understand the influence of deformation on the iron boride phases. On the left side is a wire of 5.3 millimeter, and on the right side, there is a wire of 2.3 millimeter. They all belong to S10, the material which was reinforced by 10 volume % reinforcement ratios. You can see clearly that the iron boride phases tend to elongate in the direction parallel to the cold rolling. So actually what we have done is that we have been able to control the morphology, and that we have given the iron boride phases an opportunity to change their direction by using cold rolling in the pre-sinter state, and after the boriding, they are elongated in the direction of iron boride, in the direction of cold rolling. Here is a material. Also, these images are taken from parallel to the rolling direction. Discontinuous web-like iron boride phases are formed if you use 5% reinforcement ratio. And even though they are elongated again parallel to the rolling direction as the deformation level increase, but because they are so small, they do not constitute an elongated fiber-like structure. On the left side, you see a higher deformation level. And then on the right side, you see a lower deformation level, but this is for S15. And they are high enough in the reinforcement ratios that they form in such a dense iron boride phases that you don't see the elongation effect of the iron of the cold rolling. But even then, if you see, because of these porosities are reduced when you use a higher deformation level. And these phases are also elongated. You can see this by the nature of the iron matrix here, the background. So we can see that the true effect of deformation is more visible on the S10 reinforcement ratio, because they have about 50% borided and 50% non-borided region in the core, in the microstructure. Here is again the ultimate deformation in the 1 millimeter wires. These iron particles, they were not agglomerated anymore. This is S15 specimen, which had shown the formation of agglomerated B4C particles. But even at micro scale, this is 15 micrometer, we can see iron boride phases, they are elongated parallel to the direction of the cold rolling. We can call them ceramic fibers because they are very small at the fiber scale, and you can control their morphology, and you can also control their distribution by using an appropriate reinforcement ratio in the pre-sinter state of the wires. Here I have explained the mechanism of boriding. M and N, this is pre-sinter state on the left side, and this is post-sinter state on the right side. These images are taken from the cross-section, and these images are taken from the longitudinal view. Schematic images I have made, not taken images, but actually a schematic representation. M and N particle, they combine together to form an Fe2B phases. No matter if it belongs to a different B4C particle, eventually these phases will merge, because these phases will merge together using a higher reinforcement ratio of B4C particles. You can have a higher borided region. Now, using this approach, you don't have to worry about the surface boriding, because it will eventually finish. Use an appropriate amount of iron B4C particles, and you can have a higher borided region in the core. Again, yes, sir.
If I'm not wrong, it is shown on one of your graphics. After sintering, the hardness, does it decrease? Does the hardness decrease significantly?
The hardness of the iron particles, or you are talking about the hardness of
after
iron
sintering? After sintering.
After sintering, the hardness of the sheath decreases because of the recrystallization and coarse grains which are formed. But the hardness of the core increases because of the formation of iron boride phases.
Okay, the reason why I ask is this.
Yes.
B4C is harder than Fe2B, I would say. Is it correct?
Yes, sir. Yes, sir.
Therefore, when we have, instead of B4C, we have Fe2B, then maybe it will be softer. That's what came to my mind.
Exactly. Yes, sir. I understand now. You are saying that the hardness of, you say that it is not correct to claim that the hardness of the core is increased because B4C has a higher hardness and Fe2B has a little lower hardness.
Should
be.
I mean,
yes.
my guess.
But I tell you that the B4C particles which were used in the core were so small that I must have a micro scale indenter to understand their hardness. But, and the fact that B4C particles are not there to increase the overall strength of the wires there. B4C particles are there only to serve as a boron host. That is their role in this state. And after their role is completed, and because they are small, and we have been able to synthesize these iron boride phases, I think their role is finished.
Very
and
good.
that was the purpose. Yes, sir.
What happens to carbons then?
Good question. Good question.
Cement
that is something which is under investigation right now.
Okay.
What happens to carbon is something which is something which I have tried to study more and more and more. But they say that the carbon is, because iron matrix is also in the vicinity of the B4C particles. Maybe it is dissolved in the iron matrix, in the iron matrix powders. Some say that the carbon is in the form of graphite, and because you do metallographic stuff, it works as a porosity. Many things.
Or cementite, maybe.
Maybe cementite. Cementite can be formed, but because
Fehmi can answer because he's an expert on the field. Later, I will ask him.
Okay, sir. And on the longitudinal, if you allow me, I will try to continue, sir.
Go on.
I will try to continue with the presentation, sir.
Go.
Okay. Because from the longitudinal section, you see that the host iron particle is in this state. So after the boriding, if there is no other phase in the vicinity, which will try to do the combining effect, the shape of the iron boride phases is going to be dictated by the shape of the host Fe particle. This image shows all the type of microstructure which was observed in the microscope. This is the something which you have asked. What if I boride a material which is there is no deformation and then there is agglomerated B4C particles? Well, this will happen. Large cavities will occur in the core, and the same material S15, if you deform them and bring it to 2.3 millimeter wire, the reduced porosity will occur. So agglomeration is not desired. This is also the reason we have used plastic deformation, cold rolling, to distribute the iron particles so that there is no agglomeration remained in the core. Eventually, so that you can have a higher region borided without agglomeration, higher region is borided using cold rolling. And if you literally compact them without cold rolling, you might see these big porosities. Here is the hardness of the sheets. Deformation level increases in the pre-sinter state because of the cold working. The sheet hardness also increases. But after the wires are subjected to the boriding treatment, the hardness of the wires is reduced, and they eventually show the same hardness because all wires are individually subjected to boriding treatment. These graphs are prepared to characterize and also to see whether we have actually succeeded in increasing the hardness of the material or not. So we have done a hardness scan line on the wire cross section, S5, S10, and S15 specimen. These rectangles 1, 2, and 3, they belong to, and the indentations shown here, they belong to here. For example, these red indentations are from the sheath, these two, and the remaining are from here. I will magnify them so that we can talk about this. Because a small region is borided in the S5 specimen, more number of indents belong to matrix, and a small region is borided, very few number of regions, they belong to the high hardness. It belongs to the Fe2B phases. But it is very overwhelming to see that you have a material which has a variation of such contradicting properties. You have a wire which has a sheath which is so ductile that you can bend it, but at the same time in the wire core, you have iron matrix and iron boride phases which can reach a hardness of about 1950 Vickers hardness.
Okay, 7 times larger, maybe higher. 7,
yes. 8. And as the borided region increases, more numbers try to shift from the matrix form from mode 0 to mode 2, 3, 4. And these indents, they show a hardness of maybe 2000, and at the same time you have a hardness of very small hardness in the matrix. And this picture belongs to the S15 specimen. Same logic is prevailed here. But I want to take your attention to something, which is because this thing is not that simple. On the low side, you see the hardness of the iron matrix and the sheath. And the up, you see the hardness of the iron boride phases. There are these transition zones, mode 1 and mode 5, which have a hardness in between these two. This is because the microstructure is distributed in such a way that no matter if you see this picture is taken schematically, is prepared for the longitudinal direction, and this is from the transverse direction. This is the analysis, indentation analysis. You indent the surface from here. The appearance of 0 and 1 is same, but one might have an iron boride phases right under the polished surface which you have indented. So it might show a hardness which is higher. Such a material, such a thing is more likely to be witnessed in S10 specimens because they have a 50% borided and 50% non-borided region. 2, 3, and 4, no matter what you do, if you indent them, you will see a high hardness of iron borides. Why? Because they have a supporting hard iron boride phases under the indented plane. And 5 and 1 might have a similar hardness because although it appears to be an iron boride, it is embedded in a very soft iron matrix. That is why it might show a low hardness than expected. This explains why we have also witnessed these hardness values, which are not low enough to be called iron matrix and also not high enough to be called iron boride phases. So tensile testing of the wires is reported. I have compared 000 specimen with the 400 specimen. I have checked the influence of increasing reinforcement ratios on the material. And I have compared this increasing reinforcement ratio of the B4C particles with an unreinforced 400 specimen because it does not have any B4C particles. Both of these all of these experiments are repeated for the pre-sinter and the post-sinter state And here I have studied the influence of increasing core size, again for the pre-sinter state and the post-sinter state. Okay, what we see is that the N00, this is pre-sinter state. In the pre-sinter state, I want to tell you that all the sheets are strain hardened, and they are not subjected to boriding treatment, and the cores in the wires have iron B4C particles which are very small. So we can expect that they are not going to influence the tensile behavior of the wires dramatically. So presence of a core has resulted in reduction in the tensile strength and also reduction in the strain of the wires. And increasing the core diameter in the pre-sinter wires has resulted in both reduction in the tensile strain and reduction in the tensile strength of the wires. And overall, if you see in the pre-sinter state, we cannot see that there is a dramatical difference in the tensile behavior of all wires. They have a similar tensile strength, and the tensile strength appear to be very different from each other, but please check the scale, it is 0.01 and 0.02.
100%, twice.
Yes, 100%, 100%.
Yeah, let's say twice, okay?
Yes, yes, sir. Here I have shown the influence of pre-sinter wires, tensile behavior. Diameter of the core is the one which is most influential factor which changes the tensile behavior of the wires. But when you go from 420, 520 to 620 and increase the core diameter, the tensile strength and tensile strain both decrease. This is the comparison between the pre-sinter and post-sinter wires. An overwhelming and dramatic decrease in the tensile strength, but at the same time increased ductility. It is safe to say that the sheath of the wires had very coarse grains because of the heat treatment, although we have managed to acquire iron boride phases in the core, but because of the sheath, the tensile behavior of the wire in such a way that recrystallized and coarse iron, coarse pearlite and ferrite grains have given a lot of ductility to the wires.
You mean the grain growth, is that correct?
Exactly, the grain growth and the coarse grains. I have shown you a wire sheath interface. You see there are big grains.
Okay.
Here is the comparison of post-sinter tensile behavior. The presence of the core has significantly influenced the tensile behavior in the post-sinter state more than it did in the pre-sinter state. There is an overwhelming decrease in the strain and also a considerable decrease in the tensile strength of the S400 specimen. But I want to also tell you that this was just like a needle, a 1 millimeter needle, or maybe 1 millimeter wire, 1.5 millimeter wire, which has no discontinuities, no reinforcement, no core, nothing. You try to pull it, and it will eventually break. Here you can see that again, increasing the core diameter decreases the tensile strength and the strain of the wires, and presence of the iron boride phases increase the strain of the wires, but the overall behavior, if you see here, of the wires is if they have a same core diameter, is almost similar, not very much different from each other. But is it a bad thing or a good thing? It is not a good thing. Actually, it is a good thing to see that the presence of a larger fraction of iron boride phases do not have a dramatic effect on the tensile behavior of the wires, because tensile strength is not the only criteria for the mechanical properties. We have acquired a very overwhelming high hardness in the cores of the wires, as I have shown you in the previous slide. This is again.
Zafer,
Yes, sir.
Not for composites, for bulk materials, as a rule, hardness and strength are related.
Yes, sir.
If the material has a high hardness, the strength is also high.
Yes,
but
sir.
Here we have just the opposite result. What could be the reason?
Sir, the reason is the discontinuity of the core and the sheath. It is a good thing to have a high hardness and a strength, normally they are connected, but the grains must be cohesive enough to transfer these loads to the next grain and then the next grain and the next grain when they are under mechanical loading. Then when you try to pull the wire, the first thing happens is the breakage at the interface of the core of the wire.
Yes. Okay.
And then the core behaves independently and sheath behaves independently. If you see the tensile behavior of the wire, it is only sheath which is taking all the load.
Which holds
And
load.
and it is understandable because a large fraction of the region is borided, and a very hard and brittle material, when it is subjected to tensile loading, eventually it is going to have a transverse crack like a concrete, and nothing will happen after that.
Okay.
This is I have shown you the influence of temperature on the tensile strength. It was decreased. Here is a picture from my paper in which I have reported 2 different composite wires. And indeed, they have also reported a decrease in the tensile strength after the temperature. Again, for the reasons which I have just told you, grain coarsening, rearrangement of the grains and formation of larger grains. And here, increasing deformation levels have caused increase in the ultimate tensile strength of the wires. This is also taken from the literature. So my results are not completely in disagreement with the literature.
Since our last discussion about time, 1 hour has passed.
Oh, I will take 20 more minutes and I will be done.
Go.
Okay. So this is the microstructure of the wire reinforced composites after the treatment. Good news that the wire looks cohesive enough, and we have succeeded in acquiring a microstructure in which sheaths and cores are present, how to say, in peace with each other. These microstructures are enhanced images of the wire cross sections. As you can see, that there are no discontinuities, and all those trouble which we have gone through to find appropriate temperature and pressure for the bonding, we have succeeded in increasing the.
The shapes are interesting. Are they hexagonal, more or less?
Yes, sir. They are hexagonal.
Quite interesting.
Yes, sir. The shapes are quite interesting because they are hexagonal. I will tell you that while I was writing my review, I saw that some people, they use die angles in such a way that they desire the wires to have a cross section of a hexagonal shape.
The beehives also has the same. The beehives.
Yes, the beehives also have a hexagonal shape. I have used circular wires. Okay. We have not done anything like that. So, well, in NASA, people know this better than us, I think, because this image is James Webb Space Telescope. They have used hexagonal geometries for reflecting the sunlights, for cooling the inner structure of the inner structure of the telescope. Last week, there were some images circulating on the internet. These were taken from this James Webb Telescope. Last week, just some images of the galaxies. So they have intentionally used hexagonal. Why? Because what I have studied, hexagon is a perfect shape because for joining the material, and it makes the material structurally more stable if you have a hexagon compared to a wire structure or a triangle. And without any trouble, we have used simple pressure from top and bottom, and it has caused the wires, because that structure is naturally more stable for a stable structure. So it is a good news indeed. So increasing the wire diameter, core diameter, results in a smaller section of the steel, in a smaller amount content of the steel in the wire reinforced composite states. Here you see a steel content of 1 millimeter, which reduces to 0.5 millimeter when you increase the core diameter of the wires. So now you have a hard core material, you have a softer steel matrix, and all the debris of the material which will be removed during the wear test are expected to bend, are expected to embed in these materials, and because you have a control on the cross section, you can also change the wear behavior of the wires if you use this material for a wear place, for an application in which wear applications are the primary objective. First thing is first, try to see if the iron boride phases have formed. Okay, iron boride phases have formed. They are elongated as we had expected. Good news. The microstructure of the cores at the center of the core is different from the region which is at interface with the sheath. Also, we can see that the microstructure of the sheath, which is in contact with the core, you can see these white regions, these ones. We have not done intentionally anything there, but we see that the material, that the sheath which was in contact with the core has grains, but they don't have any perlite structure there. You can see it in all wires. And that is called zone 1. Zone 2 is the region which is, zone 3 is the region which is at interwire boundaries. There too, we can see that there are formed these bands, no perlite structure there. Also at interwire boundaries, no perlite structure there. So they are carbon deficient region. Here is a cross section of the wires, wire A, B, and C, and this O region is the place where they are bonded. So I have divided the whole microstructure into 3 zones. Zone 1, which is small and loosely bonded iron boride phases. Zone 2 in the sheath is carbon deficient region, and zone 3 is also interwire boundaries carbon deficient region. This is a summary of the microstructure. All features of the microstructure are given here. So while we needed to see what is this thing around the wire core and what is going on there. What we saw is that the iron boride phases actually have formed there, but they are loosely bonded and they are not as cohesive and as dense as the iron boride phases in the core. And the ferrite sheath, which was in contact with these cores, they don't show any perlite phase. Here is an interwire boundary. Here is an interwire boundary region. They also show no perlite phases, and only iron borides or only ferrite phases have formed. In the SAM micrograph, you can see it not very clearly, but in the optical micrograph, it is very clear. So we needed to see what is going on. So we did an EDX analysis running from one wire to another wire, and we saw the carbon content in the wire at the interwire boundaries was lower as compared to the region belonging to the different wires. So we can say that these regions, safely say that these regions are indeed carbon deficient regions. Why they have formed? Well, why they have formed? Well, that might be because of the diffusion of carbon from the sheath to the cores at the region of intercore wires. Similar thing has been reported for the surface boriding, but that is a completely different phenomenon. What happens there is that after the formation of the iron boride phases on the surface, there are some regions right here, which is known as the transition region. Their complete diffusion of boron is not complete diffusion of boron to the host iron particles, to the host iron steel is not happened. That is why there are softer regions which are formed. High hardness region, low hardness region, and substantially low hardness region in the host. And the fact that we can see these carbon deficient regions in the sheath, we can claim that maybe carbon has diffused into the iron particles here before the boriding process could start. So for that claim to be true, we must characterize their hardness. So we did a hardness analysis of the core. The hardness of the core was really high. The hardness of the transition zone, zone 1, is low, and the hardness of the zone 2 is very much low because it is just ferrite phase.
Further lower, yes, it must.
Yes, and then the interwire boundaries we see perlite, ferrite, perlite, and then interwire zone has also only ferrite phases. This is these images show the typically the same stuff which I have just done, which I have just said. Interwire boundaries, high hardness, low hardness, high hardness, and interwire boundaries, low hardness. Core, substantially high hardness. Zone 1, a little low, and then lower hardness. And while people were reporting the hardness of these transition zones, which are formed because of the presence of elemental elements in the steel, they have also reported low hardness in the transition zone. And these are some studies which have reported the hardness of this formation and hardness of these materials. Last few slides of this presentation. So we have cut the specimens, if you remember, in these planes, and depending upon the cutting plane, we can see that the wire cores, dark colors represent the cores, and these are interwire bands. They were exposed. So we were able to see the type of cracks which were formed in which component of the wires. Which components of the wire reinforced bulks. These are the results of the wire reinforced bulks 3-point bending tests. Quite interestingly, the B00 specimen has behaved extremely ductile, and the B400 specimen has substantially low load and it fails very quickly. So the claim which we made up while studying the tensile behavior of the wires, the geometrical discontinuities are a very important phenomenon which must be taken into account while doing the bending tests.
You mean between the core and the seat?
I mean the wire core diameters of the wires which have constituted the wire reinforced components substantially influences the bending behavior. Here is another example. Increasing the core diameter reduces the load at failure and also the length. And here I have compared, if you don't see this, this one, 410, 415, and 420, they have all in situ boroided phases. Their bending behavior appears to be similar. And the one 400, it does not have any boroided cores. So it has a lower load and a lower extension. Again,
pre-sinter or after sintering? These
are in the bulk form, so they must be sintered.
After sintering, okay.
Of course, because of the presence of iron boride phases. Sir, the presence of B4C particles are not going to influence the bending behavior very much, because the size ratio between the particles, between the iron and B4C particles is so big that before all the B4C particles do is that they are embedded, present in the interparticle boundaries. So I don't believe they are going to change the mechanical response of the material.
Zafer,
yes,
maybe they may behave as stress concentration factors. Maybe
they might have, but this is something which I believe. Maybe this is not the fact, but I believe that if we had done the same experiment, only in the pre-sinter wires being together, we might have not seen their influence very much. But even with the presence of iron boride phases, there is not much difference between the 10, 15, and 20%. There is only difference because of the presence of iron boride phases, not because of the ratios of iron boride phases. So here I have shown the types of stresses which are induced because we have 3 layers of wires. Which layer is going to be exposed to which type of stresses I have reported here. Top compression, middle shear, and bottom is tension. So I have studied side views for the fractography and the top views with the electronic microscope. So these 2 types of views which we have studied for the fractography. This is interesting to see. After the bending, this specimen was elongated very high. So there are no cracks formed here, but the surface shows a material which is subjected to tension, a typical steel. After tension, tend to show a structure like this. And we can see that the cracks which are formed in the transverse direction, when they reach the interwire boundaries, they tend to change instead of being transverse to the longitudinal direction. So I have, after these observations, I have taken these notes. Cores are preferably failing with the transverse cracks, no matter if they are under tension or no matter if they are under shear. That means that the cores which belong to the lower wires of the material, they fail in transverse here. And the interwire and the sheath core interfaces, these are interfaces. The sheath core interfaces and the interwire interfaces, the diffusion bonded interfaces, they fail with the longitudinal cracks. Here you can see, again, this can be said that the transition zones which were loosely bonded iron boride phases, or maybe the presence of ferrite phases at the sheath core interfaces at the interwire boundaries might have caused to fail them in longitudinal, because shear stresses tend to change. It tend to break them at the most weakest area. Here is a specimen which has larger cores. Again, we can see that the sheath and core interfaces, they fail in a longitudinal cracks, but the cores, they fail in a transverse cracks. The region which is under tension is majorly influenced by the tensile stresses in the bottom layer, but the region which is exposed to the compressive stresses is influenced. A very small region is influenced with those type of stresses. Here you can see, I showed you the bottom plane that the cores were failed with the transverse cracks, but it can also be seen that the middle layers also cores are preferably failed with the transverse cracks. But the sheaths, it does not happen. In the sheath, if you see, sheath is more compliant to the type of stresses. If it is exposed to compressive stresses, it fails under compression, and if it is exposed to the shear stresses, then it will have this type of failure mode, which is typical of a shear stress failure. This picture is prepared to show that the cracks which are produced in the wires, in the sheaths, they are independent of the cracks which are produced in the cores. This image is prepared by an image analysis in which the bottom layer is painted in blue and the top layer is painted in green using the pixel information. Blue is underlayer, and this crack, which was formed in another wire, this bottom wire, it has propagated to the next wire. So if such a big transverse crack in the sheath occurs, the material fails before the core could do something. The load is reduced and the material fails because the cracks which are formed in the wires, they do propagate into the next wires. Here also transverse cracks in the core, and the sheath's shear face A and shear face B shows that this is an interwire boundary, that longitudinal cracks are formed in the sheaths. Same thing, but I want to say that the compressive stresses result in the longitudinal cracks in the core, in the top layers. Again, longitudinal cracks are seen in the cores only when they are subjected to the compressive stresses. Under tension and shear, here and here, they always develop transverse cracks. But I want to draw your attention to this region. This is interwire boundary region, which does not have any cracks. So can we say that the wires which have a core diameter of 6 millimeter, the cracks at the interwire boundaries, they are not formed because it has a strong interwire diffusion interface. We can say that, but the region there are not seen any cracks at the interwire boundaries does not have anything to do with the strongness of the bulk material. It has something to do with the preference of the formed cracks in the material. Because if this was the case, that larger core diameter result in a stronger interfaces, then
they would be stronger even, but they are
then we
not.
would have not seen anything like this. This is a same material which has lowest failure load. It has something to do with the preferences of the cracks. That can only be seen if we go for the transverse analysis. Transverse analysis of the wires is shown here. What we saw there is something which we saw here also. Sheath core interfaces most vulnerable to the bending stresses. Interwire interfaces most vulnerable to the bending stresses, and they fail because you see these cracks. This was 4 millimeter inner core diameter. This is 5 millimeter inner core diameter. Again, interwire interfaces fail, sheath core interfaces fail, and similar things happen here also. But when we go to the B66 specimen, we see that the sheath core interfaces also fail like this, but the interwire boundaries of the wires, they do not fail. So actually it affirms the observation which we had while viewing from the side view. So what could be the region that we don't see an interwire fractured region, but still the stress of the material, the strength of the material is very low, that it fails at very lower loads. This is because of this stuff. We have larger cores, and before the material could withstand a bending load, these larger cores fail with transverse cracks more preferably, and the region fails at that load value before the failure of interwire boundaries. Not because they are strong, it is because they are not preferably fractured under the bending stresses. So this is the summary of the cracks. Shear longitudinal cracks are formed at interwire boundaries and sheath core interfaces, and we expect a material like this. And the transverse cracks, they are formed in the core, and if a transverse crack is formed in the wire, and the fact that I have proved that the transverse cracks formed in the wires are propagated to the next wire, you see a mode 1 failure, an immediate failure. Such an immediate failure in the material will result a sudden decrease in the load value, which is seen here, right here, something like this, but they have to be in synchronization so that all wires can fail at the same time. So there is a sudden decrease in the load value. So all these modes which I have explained here, they are mapped on the graphs if someone wants to see what type of failure might have occurred in the material. Achievements of these studies, we have shown a manufacturing method, a thermochemical approach, which uses plastic deformation and powder metallurgy to make composite wires which are reinforced with ceramic phases. Hard diffusion bonding and in situ boriding is used for the first time to make wire reinforced bulks. No squeeze casting and no fiber foil type approach is used. So it is a new manufacturing approach. Micro manufacturing of manufactured materials you have already seen, but I have manufactured. I will skip that. And characterization of the microstructure is done by the image analysis of particles, which has not been done before. And I have reported the core deformation behavior of particles. The methodology is presented to see how the particles are going to behave and what type of material, what region of the material is borided using the image analysis. Then the influence of boriding and hard diffusion bonding on the microstructure is also reported. And in the last section, we have used tensile and wire reinforced and the bending test to characterize the mechanical properties of manufactured material. Applications and scope. Wires can be used as strengthening elements in metal matrices just the way they use aluminum wires in metal matrices for their strength. Our wires are not only strong, but they also have high hardness, so they can be used for a specific functionality. The specific functionality basically revolves around the tribological applications and the wear applications. Why? Because the phases which have been used in this study are basically used for the wear, corrosion resistant, and tribological applications. And the reason that a softer material is combined with the contradicting high hardness of the material, while the wear tests are occurring, the debris during the wear applications, they can be embedded in the softer sheath and after in the softer steel, and we can prevent the three-body abrasion in such applications. And there is going to be a continuous supply of iron boride phases, no matter how long you use the material, unless it finishes, unlike the surface borided materials, in which eventually the hard layer of the material is removed, and the hard layer of the borided steels is not connected cohesively with the host material. In the material which I have used, such a thing is not an option, because all wires are cohesively controlled. But the drawback of my material is that if you are going to push the material into a loading state in which the shear stresses are going to be the dominant loading conditions, my material can fail at wire core interface, at sheath core interfaces and interwire boundaries. That is because of the presence of software ferrite phases at that area. Thank you for your time.
Thank you, Zafer. Have a breath.
Okay, sir. Thank you.
Yes, gentlemen, if there are extra questions, you may have. If not, we will discuss the presentation. Tamam, o zaman eğer soru yoksa Zafer'i yine dışarı alalım. Recep Hoca, sen miydin host?
Evet hocam. Yani ben son bir cümle olarak isterseniz hocam.
Tabii buyurun.
Zafer, so iron boride is undesirable fast, as I understand.
Yes, sir.
You researched its effect on the structure by controlling it, right?
Yes, sir. Yes, sir.
So I would like to give an advice.
Yes, sir.
Future studies.
Yes, sir.
Future studies.
Yes, sir.
You can turn the results you have into a receipt and present them to practitioners by expanding your studies in future. Okay.
Yes, sir. Okay. The first thing is I think we are going to use this material for the wear tests. First thing is first. Okay. The manufacturing part is complete now. I think we must go from here for the wear test so that we can actually see what is going to happen with if we subject them to the wear test, how the structural configurations are going to behave, what type of things can happen. So we are thinking of expanding this research in that direction. Thank you for your suggestion also.
Okay, you can take the future studies. Okay.
Yes, sir.
Thank you.
No problem, sir.
Sedat Hocam, kolay gelsin.
Buyurun hocam, dinliyoruz.
Zafer, thank you very much for good presentation. There is one question to you.
Yes, sir.
What is your opinion about the hardness of iron bore and iron 2 bore?
Yes, sir.
About which one is the hardest, the highest hardness value?
Sir, the high hardness is high boride phase, FEB, not FE2B.
Yes.
The high hardness is good thing, but it is very brittle. All the cracks which are formed in the material are because of the presence of FEB phase. Also, the thermal expansion of FEB phase is different from the FE2B phase. In my thesis, I have made a table in which I have shown the contradicting properties of both phases. So FeB phase is very hard and brittle. That is why it is not desired.
Your study, in your study, there is a iron ore phases. Maybe.
Yes, sir. Yes, only Fe2, only low boride phase.
Yeah. Thank you.
Yes, sir. Hocam bana ekran paylaşmama izin verebilir misiniz müsaadenizle?
Paylaşabilirsin Numan.
Hocam buradan oraya nasıl geçeceğim? Bir saniye. Hocam çok özür dilerim. Ben bu konuda çok tecrübe değilim sanırım.
Hangi konuda bu konu derken Zafer?
Hocam bu tamam hocam. Buradan share screen. Bak, ekranım geliyor mu hocam?
Evet, görüyoruz ekranı.
Tamam hocam. Hocam görebiliyor musunuz?
Evet,
Solda
evet.
bir tane tablo var.
Evet.
Burada hocam, here I have explained the properties of FeB and Fe2B phases from different references in which the contradicting properties are shown. If you see the thermal expansion of this one and this material is very different. This is 7.8 and this is almost 3 times higher. This one is compressive and this one is style, and also I have shown the structure, melting points, other details of this material. Because of this thermal expansion difference, the formation of FeB phase is not desired. It is a high hardness material.
Yes.
Ben buradan hocam söz alabilir miyim? Devam edebilir
Yes
miyiz
Mustafa,
buradan?
tabii.
Ben Türkçe soracağım ama Zafer'in
Türkçe'de
İngilizcesi kadar
sorabilirsiniz. İngilizce sorabilirsiniz.
güzel olduğunu inanıyorum hocam. Türkçesi de güzel, Zafer'in. Burada peki demir borunun oluşmadığını gözlemlediniz değil mi? İş yapıda.
Evet,
Demir
metalografik olarak onun oluşmadığını
boru.
fark. Doğrudur.
Bunu kontrollü olarak mı yani sağladınız, yoksa yani %20'ye takviye oranına kadar kendisi mi oluşmadı? Yani oluşmamasını siz mi temin ettiniz demir borunun? Yoksa...
Evet, biz demir borunun bu takviye oranları kullanarak önlemeye çalıştık. Amacımız oydu. O faz orada oluşmasın diye. Bunun için de faz diyagramlarından uygun olan takviye oranlarını kullandık.
Evet, anladım. Aslında şöyle de desteklenebilir bu. Yani takviye oranı %20'yi geçseniz dahi acaba oluşur muydu, oluşmaz mıydı? Ona da bakmak gerekiyor.
Doğrudur.
Yani düşük takviye oranlarında partikül boyutunun da önemi var biraz. Küçük mikrona, yani küçük partikül boyutunda bir bor verici ortam var. Belki %5 oranında partikül boyutunu 5-10 kat artırdığımızda bile o bor partikül etrafında demir bor oluşumunun belki gözlemlenebileceğini biz daha önce tespit etmiştik. Yani takviye oranından biraz da bağımsız bir hale gelebiliyor aslında demir borunun oluşması. Ama sizde oluşmamış tabii. Yani partikül boyutu küçük çünkü 1-7 mikron arasındaydı.
Doğrudur. Onun sebebini de şu şekilde.
Evet.
Onun sebebini şu şekilde düşünüyorum. Eğer biz büyük tanecik kullanırsak, mesela B4C partikülümüz çok büyük olursa, orada mikro boyutta düşünerek biraz makro boyutuna geçersek, sanki orada yine B4C partikülün içinde bir difüzyon bariyer oluşuyor. Belli bir süre sonra B4C partikülün içinde kalıyor. O durum büyük parçacıklar için gerçekten de geçerlidir. Orada artık takviye oranı çok önemli olmuyor. Çünkü makro boyutta bakmıyoruz olaya. Partikül boyutuna bakıyoruz. Partikül boyutuna baktığımızda orada bir diffusion bariyer oluşuyor ve o B4C partikül sadece F2B fazı değil, FEB fazı da oluşturuyor ama sadece FEB fazı oluşturmuyor. Aynı zamanda orada kalıntı bir B4C partikül oluşuyor. Biz kalıntı bir B4C partikülün çok oluşmasını istemiyoruz. Çünkü böyle bir durumda o bağlanmadığı için kimyasal olarak malzemenin içinde sıkıntı yapıyor. Sizin çalışmalarınızda da bunları gördük. Biz daha önce vardı yani böyle bir şey. Ama partikül boyutu çok daha önemli bir faktör. Onu gözümüzün önünde bulundurarak biz sadece partikül o kadar küçük olsun ki bu tarz olaylar olmasın. Küçük partikül boyutunu kullandık.
En mantıklısı da buydu zaten. Doğru, güzel olmuş. Hem de şeyi de önlemiş aslında. Gözeneklilik oluşumunu veya aglomerasyon oluşumunu önlemiş.
Doğrudur.
Evet, aklımda birkaç soru daha vardı hocam. Vakit var mı? Yani bir iki tane fazla yok ama
Sor
sorabilir
tabii.
miyim?
Zaten 2 saat harcadık. 10 dakikada harcarız yani tabii.
Ama aklıma takıldı da o yüzden. Belki ben algılayamadım. İngilizce hızlı konuşabildiği için Numan. Güzel bir nokta vardı hocam orada. Borlanmış bölgelerin görüntüsü olarak analizini yapmıştı galiba. Alansal olarak hesaplayabilmiş onu. Onu hani sertlikle veya diğer gözeneklilikle ilişkilendirilebilir mi acaba? Güzel yani bizim aklımızda da vardı daha önce de böyle bir çalışma. Olabilir mi diye. Ona değinmişsin, güzel olmuş ama o yani iç yapıdaki borlanmış bölgenin alanıyla takviye oranı arasında veyahut da sertlikle arasında bir ilişki kurulabilir mi? Kurulabilirse çok güzel olacak yani bu. Yani doğrusal bir bağlantı oluştu mu yani? Takviye oranı arttıkça aynı oranda da borlanmış bölge alanı arttı mı? Veya da hacim olarak, yüzeysel olarak da olabilir bu, metrekare olarak ya da santimetre kare. Veyahut da
Biz,
hacim olarak bir
biz
bağlantı kurabildin mi?
Hocam biz malzemenin sertliklerine baktık ama daha çok 10 gram, 20 gramdan yukarı çıkmadık. Sizin dediğiniz çok mantıklı bir sonuç olabilirdi. Eğer
Evet.
%5'lik, %20'lik borlanmış bir öz ile %85'i borlanmış bir özün arasında onların sertliklerine bakarsak ama bu sefer sertlik izinin gramajını yükseltmemiz gerekiyor. Mesela
Evet tabii ki.
20
Genel
değil
tabii
de 200 olsa
sertlik.
o
Tabii,
zaman makro boyutta onun sertliklerinin
tabii.
o olayla ilişkilendirilebilir. Yani ve tabii ki daha yüksek bir sertlik gözükecek orada. Yalnız ben partikül boyutunun üstünde çalışma yaptığım için partikülün üstünde nasıl borlanma oluyor? Ben o kadar yüksek makro boyutta sertliklerine bakmadım. Bakmak isteksek bakılabilir ve o daha çok borlanmış olan bir bölgenin sertliği normal az borlanmış bir kordan çok daha yüksek çıkacağına inanıyorum. Sebebi de
Anladım.
oradaki bor fazlarının daha yoğun bir şekilde oluşması.
Tabii evet. Aynı şekilde gözeneklilik üzerinde de böyle bir bağlantı kurulabilir. Ya da hesaplanabilir. Evet, orası güzel. Bir diğer sorum da şu olacak. Genel olarak yani bilinmesi gerekiyor tabii ama ben sana soruyorum. Belki değinilebilir orada. Yani in situ yöntemiyle böyle bu şekilde bir yani faz oluşturarak sertleştirme yoluna neden gitmek istediniz? Yani hangi avantajları var in situ ile sertleştirmenin? Yani bunun dışında yayınıma uğramayan sert bir faz da atılıp sertleştirilemez miydi takviye olarak? In situ olarak yani hangi avantajından yararlanmak istedin?
Ben hocam sorunuzu tam anlamadım. Yani in situ
Hı
olarak
hı.
kullanırsak da niye yüzey sertleştirici bir malzeme kullanmadık
Evet.
diye mi karşılaştırma yapmamız gerekiyor?
Şimdi iç yapıdaki evet öz kısmını in situ yoluyla faz oluşturarak sertleştirmek istemişsin.
Doğru.
Bor yayınabiliyor demire.
Doğru.
Bunun dışında yayınmayan farklı bir sert bir partikül, seramik karakterli yayınmayan. Demirin içerisine yayınlayan bazı sert karakterli malzemeler de olabiliyor seramik. O partikül takviyesi yapılarak da sertleştirme yoluna gidilseydi eğer, ekstrüzyona tabi tutsaydık ve gene difüzyon yoluyla bağlasaydık bu telleri, olur muydu sence? Ya da
Onun oluşması
yani
için bakın
genel olarak institünün avantajları ne olabilir yani sence?
in situ'nun avantajı benim
Evet.
çalışmamda eğer kimyasal olarak bu partiküller yüksek sıcaklıkta birbiriyle bir etkileşim yapmıyorsa onun bir esprisi yok. O zaman sadece ilk başta bizim kullandığımız sert parçacıkları sadece sadece onların dağılımı değişecek ama onun sertliği ve borlanmış alan gibi büyük bir bölgede o sertlik yayılmaz. Parçacık bulunduğu yerde sertlikte bir etkisi görülebilir ama partikülün bulunmadığı yerlerde bizim fazların oluşturduğu gibi in situ kullanmazsak büyük bir bölgede sertlik artımı gerçekleşmez. Bunun için kimyasal bir yöntem gerekiyor. Bu sert fazların in situ elde edilmesi gerekiyor ki biz korun büyük bir bölgede sertlik arttırma etkisini ortaya çıkartalım. Partikül bulunduğu yerden ne geometrisi değişebilir. Sadece orada geziyor ve çok seramik partiküllerin en büyük problemi şunu sorabiliriz. Madem öyle bir problem varsa biz %50 seramik partikülleri kullanıp yine telleri üretebiliriz ya da şey yapabiliriz. Hayır,
Evet.
seramik partikülleri kendi yaralarında bu tarz deformasyona maruz kaldıklarında birbirini kırabiliyorlar. Büyük parçayla başlayıp küçük parçacıklara kadar geçebiliyoruz. O yüzden kimyasal ve in situ yöntem bu tarz uygulamada en uygun yöntemdir diye düşünüyorum.
Evet tabii.
Peki burada bir de işte arayüz olarak seramik oluştu.
Arayüzeyi.
O
Evet,
avantaj
arayüzeyi bağlı.
olabilir. Yani öbüründe
Evet, evet.
iki faz arayüzü çok keskin bir geçişte oluşurken burada iki faz arasında bir ara faz var. Ara geçiş.
Evet, evet,
değil mi?
evet, evet. Yapısal süreksizlik söz konusu yani.
Yani.
Yapının içinde o tarz yapısal süreksizliklerin ben bu kadar etkili olacağını düşünmüyordum ama ben çekme testlerinin sonucunda baktım ki aynı malzemenin içinde sadece delik yapıp içine tekrar aynı malzemeden doldursanız bile çekme sırasında, mekanik bir loading sırasında ilk önce kırılacak yer orası olur, sonra ikisi birbirinden bağımsız hareket eder. Yapısal süreksizlikten dolayı sizin dediğiniz gibi problem çıkabilir yani.
Ya hocam izninizle bir son sorum daha olacak da soğuk olarak herhalde şekillendirdiniz değil mi? Patteleme
Tabii
yaptınız galiba.
doğrudur. Eğer bunu soğuk olarak şekillendirmeseydik
Evet, nasıl başarabildiniz? Yani başlı başına ayrı bir problem. Demir çünkü kullandığınız kılıf olarak. Oda sıcaklığında çok yani 8 milimden yaklaşık 1-2 ne milime kadar çapı indirmişsiniz. Herhangi bir iç yapıda veya dışarıda yırtılma, kırılma gibi problem oluştu mu? Ben çok merak ettim yani bunu. Hem
ben
öz ve
size
kılıf arasında evet. Onu nasıl
e,
sağladınız? Yani hiçbir
onu
hani yırtılma oldu mu, olmadı mı? Dışında veya iç kısmında.
bizim tellerimiz Fehmi Hoca iç kor şeylerini çok uygun bir şekilde seçmiş. Sadece kor diameterleri yüksek olsa çok ince bir kılıf kullansak ikinci rollingden sonra bakın bir şey anlatmak istiyorum Mustafa Hocam.
Muhakkak.
Bizim
Tabii.
malzemelerimiz, bizim
Sadece
toz
teorik bilgi
karışımlarımız.
öğrenince vardır onun geçmişi ama biz sadece öğrenmek istedik tabii.
Hocam biz toz karışımlarını bir telin içine koyup çekmeye başladığımızda belli bir süre kadar bu tozlar birbiriyle sıkışır. O
Evet.
süreden sonra mesela 5 milimetreye kadar geldin sıkıştılar. Artık sen onları sıkıştıramıyorsunuz. Sıkıştıramadığımız zaman Mustafa Hocam.
Tabii.
Onun bir
Sıkıştırabildik.
sonraki deformasyona daha fazla deformasyon yapmak istersek bu sefer kılıf plastik deformasyona uğramaya başlıyor. Ben böyle bir şey gördüm. Belli bir süre sonra plastik deformasyonu kılıfta oldu. Kılıfın sertliği belli bir deformasyon oranına kadar yükselmiyor. Ondan sonra aniden yükseliyor. Eğer orada ince bir kılıf kullansak o kırılır. Ondan sonra kılıf oradan kaybolur ve toz karışımları dışarı çıkar. Tamamen
Evet.
amacı dışına şey yapmış olur. Onun için biz çok ince kılıf da kullanmadık ve çok kalın kılıf da kullanmadık. Farklı kılıf kalınlıklarını kullandık. O şekilde de eğer plastik deformasyon olmuş olsa bile kılıf içinde o kadar kalındı ki biz onun etkisini görmedik. En korktuğumuz 6 milimetrelik en korktuğumuz 5 milimetrelik kor çapı olan tellerde kılıflarda bazı yerlerde incelme vardı. Ama ciddi bir kırıklık ve bağlantı konusunda bir şey yaşamadı. Bunu nasıl gördük? Biz kestikten sonra microstructure'larına baktığımızda gördük ki tüm yapının kılıfı da var, koru da var, bağlanma da var.
Güzel, başarılı. Hocam son bir sorum daha olacak eğer müsaadeniz olursa.
Sonra son diyorsun da son deme yani.
Hocam sadece hocam başlığa baktığımız zaman ilk algı olarak şey oluşuyor. Yani bir toz veya sıvı infiltrasyon yöntemiyle üretilmiş bir malzemenin içerisine tel bir filamentin geçirilmiş olduğu yani filamentlerle desteklenmiş bir kompozitin bu şekilde değil de ilk oluşturduğu algı yani bir toz içerisine eklenmesiyle üretilmiş olduğu gibi algılanıyor. Belki orada bir revizyon gerekebilir. Yani başlıkta veya diğer özet kısımlarında. Burada sanki yığma veya eklemeli veya da difüzyon yöntemiyle tellerin birbirine kaynaklanması veyahut da bu şekilde üretilmiş bir malzeme hocam bir revizyonu gerekebilir mi acaba bilmiyorum.
Başlık değişik önerisi vardı orada ama
Tamam.
onu okumadık herhalde. Var.
Onun dışında bir şey yok.
Zaten başlıkta tamamen malzemeler farklı. Bakır vesaire,
Evet.
bakır grafit olarak bahsediyor. O başlık tamamen değişti. O bir formumuz var. Başlık revizyon formu. Onu biz size atmadık. Harun hocamdan geldikten sonra onaylamanız için. Onu görmediğimiz için başlığın değişimini talep edeceğiz şeyde. Test kontrol formunda. Haklısın, doğru.
Onun dışında hocam teşekkür ediyorum. Vaktinizi aldım ben de.
Evet. Başka soru?
Benim için
Tamam. Son soruyu ben soruyorum o zaman Zafer. Bu soru aslında hani Türkçe soracağım ben de.
Buyurun hocam.
cevap vermeyebilirsin aslında. Çünkü tam senin işle bağlı değil.
Buyur hocam, baş üstüne.
Şimdi B4C olduğu zaman bağlar kovalent. Kovalent bağları var.
Doğrudur, doğrudur.
Burada demir ve boron olduğu zaman demir metal bağlar var. Öbürünün kovalent var. Aradaki bağın türü ne? Kimyasal olarak da demirle boron arasındaki bağ.
Hocam şeyin atomları küçük ve B ve C atomları çok küçük. Onlar kendi aralarında tabii ki kovalent bağ oluşturuyorlar. Burada ben okudum onu.
Kovalentin
Belli bir
o
süre
bir ilgisi yok. Onun elektronlarla ilgisi yok. Ben de öğrenmek için merak şu anda aklıma geldi. Yani kovalent değil, iyonik değil, metalik değil. Ne olabilir Fehmi? Senin de fikrin var mı? Şu anda aklıma
Hocam
geldi.
solid solution olabilir mi hocam?
Şimdi şey var. Siz demir borur bağını kastediyorsunuz zannedersem.
Evet, evet.
O demir borur fazı bir seramik fazdır. O intermetalik ya da seramik grubu olarak kabul edilir. Yani o faz bir seramiktir. Nasıl ki
Seramik olarak kabul
bir
ediyor.
çeliğin içerisindeki sementit gibi demir borur da bir bileşeni demirdir, metaldir, diğer bileşeni metal dışıdır. Dolayısıyla kimyasal tanım olarak tam bir seramiktir.
Seramik.
Dolayısıyla bağ yapısı olarak seramikler biliyorsunuz hem kovalent hem de iyonik bağ tek
Ortak
başına ya da ikisinin karışımı
ortak
olarak
özelliklerini taşıyor.
oluşturabiliyorlar. Evet.
Tamam, teşekkür ediyorum. Hocam başka sorunuz yoksa Zafer'i alalım hattan. Recep Hoca, sizde miydi?
Hocam ben jüri üyesi dışındakileri çıkarıyorum.
Yani işte onları söylüyorum. Evet.
Onları bekleme odasına alayım ben.
Evet.
Tamamız herhalde.
Saniye
Hocam
hocam.
ben buradayım, beni çıkartın isterseniz.
İşte numaran da kaldı.
Bir saniye.
Harun hocam size ses kapalı kalmış.
Bir saniye hocam.
Harun hocam sesiniz kapalı kalmış.
Tamamdır.
Mustafa hocam senin de sesin kapalı.
Evet hocam şu anda 5
Tamam.
kaldı sadece.
Evet, yine misafirimizden başlayalım. Harun Hoca'dan değerlendirmesini alalım.
Teşekkür ederiz. Çok güzel bir çalışma olmuş. Ben tebrik ederim Fehmi hocamı. İyi bir çalışma yapmışsınız hocam. Tebrik ederim. Elinize sağlık. Gördüğüm kadarıyla zaten 2 tane güzel bir yayın yapmışsınız. Bir tane de review olan bir yayınınız var. Olacak yani hakemlik süreci devam eden bir çalışmanız var. Benim için olumlu, güzel bir çalışma. İyi de sundu. Konuya da hakim arkadaş.
Evet.
Ve yeterli görüyorum Sayın Hocam.
Teşekkür ediyorum. Mustafa Hoca.
Hocam ben de katılıyorum hocama. Kapsamlı, detaylı, güzel bir çalışma. Teşekkür ediyorum. Benim için olumlu, ben de başarılı görüyorum.
Recep Hoca.
Hocam ben de aynı görüşteyim. Güzel bir çalışma. Artı farklı olarak temiz yazılmış bir tez olarak. Yani çok fazla hata da bulamadım işin açığı. Hayırlı olsun diyorum hocam. Ben de.
Teşekkür ediyorum. Evet Fehmi Hoca. Zaten Fehmi Hoca'nın çalışmalarını
Evet.
biliyorum. Bizim de buna benzer bir çalışmamız var.
Evet. Evet hocam. O
Dolayısıyla
paralelde bir çalışma.
ilgiyle
Evet.
izledim, takip ettim.
Evet.
Harun Hoca'nın dediği gibi olaya da hakim Zafer. Fakat Zafer'e ben bir şey söyletmek istediğimi söylemedi yani. Ben ticari olarak da bunu burada kullanacağım diye böyle kendine güven bir şey de bekliyordum. Onu biraz geniş alana yaydı.
Evet.
Aslında bizim bilim adamlarında o eksiklik var. Aslında evet arkadaş ben bunu şurada kullanacağım deyip icabında gerekli mesajı da vermek lazım. Güzel yeni bir çalışma oldu. Teşekkür ediyoruz. Fehmi'yi de tebrik ediyoruz. Fehmi Hocam.
Teşekkür ederim hocam. Hocam ben son olarak siz başta olmak üzere tüm jüri üyesi arkadaşlarıma teşekkür ediyorum. Tezi sabırla okudular, değerlendirdiler, sınava katıldılar. Hepsine emekleri için teşekkür ediyorum. Son bir vakit olarak da Hafız, onların belki biraz Pakistan'da adet bu tür şeyler, bir cübbe giydirme töreni yapmak istiyoruz, küçük bir tören.
Evet.
Online nasıl olur bilmiyorum. Şimdi odama davet edeceğim. Burada ve kamera önünde hem kendisine siz açıkladığınızda, sonucu açıkladığınızda arkalarında bir küçük bir cübbe giydirme töreni yapmak istiyoruz müsaadenizle.
Gayet güzel olur.
Evet, güzel olur. Memnun oluruz.
Geçelim. Baki Hoca da yapmıştı öyle bir şey hatırlıyorum.
Evet, yani şeyde oluyor. Fiziksel
yama-
ortamda olsak daha
Evet.
kolay olurdu ama online olarak şimdi kameranın açısını ona göre ayarlayacağım. Umarım sıkıntı olmaz.
Hocam o zaman Fehmi Hocam siz odanıza davet edin. Ben tekrar oradan çağırmayayım.
Öyle mi yapalım? Tamam.
Kaydı durdurdunuz mu Recep Hoca?
Kaydı durdurayım mı hocam?
Tabii artık kaydın işi bitti yani.
Durduruyorum kaydı hocam.
Evet.
Buraya gelmedi. Ya, maalesef bizim bir şeyimiz yok. Şey alsın.
Zafer, welcome back again. Do you hear me?
Yes, sir.
Okay, I will speak very shortly, okay? The jury assessed your presentation
Yes, sir.
and unanimously, with flying colors, you succeeded.
Thank you, sir. Thank
We
you.
found
very
you
much.
successful. Your defense, it was very good. Congratulations.
Thank you, sir. Thank you.
From
very
now on,
much.
you are a doctor. Okay?
Thank you.
I thank you. Okay.
Thank you, sir. Thank you.
Now, I think Fehmi will tell you that he's planning to prepare a small, okay,
Okay.
taking a, what we call a coat, okay, doctor coat. What do
Yes,
you call
sir.
it?
Yes, sir. Yes, sir.
Okay.
Döndürüyorum.
Dressing.
Hocam, kayda almıyor mu hocam?
Yes, yes, yes. Onu sordum.
Şey gösteriyor mu? Nereye gösteriyor şu an?
Şurayı gösteriyorum.
Zaten olması lazım. Nasıl alıyoruz? Gel. Evet, maalesef şeyimiz yok. Şöyle en azından bir sen şöyle geç. Oradan daha net gözüküyordur. Gel, şöyle gelsen gel.
Sen, tamam şimdi gözüküyor.
Bu konuşmalar alıyoruz.
Congratulations.
Çok teşekkür ederim.
Gel yine. Son bir şey söylersen.
Kapatayım mı hocam?
Sen takı son bir şey yapıyoruz. Zaten kapatacaktır.
Saygıdeğer hocalarım, çok teşekkür ederim ilginiz için, zamanınız için. Ben 2009'dan beri Erciyes Üniversitesi'ndeyim. Ve sevmeyerek okuduğum bir bölümden çok güzel sevdiğim bir bölüme geldim, makine mühendisliğine. Ve bu aşkı ve sevgiyi arttırmakta hocamın çok fazla katkısı var. Mikroskopu ilk kullandığı, nasıl kullanmam gerektiğini bile anlatmıştı bana, o günden beri hatırlıyorum. Sonra numune parlatmaktan buraya kadar geldim hocam. Çok imkanlarını ve ilgisini çok verdi bana. Okul olarak üniversite ve sizlerde sizin güler yüzünüzün çok büyük bir katkısı var. Kapıdan çevirmemenizin, ilginizin ve buradaki yaptığımız işe değer verdiğiniz için bu önemli bir iş. Bunun bize de yani farkındalık yarattığınız için çok teşekkür ediyorum hocam.
Biz
Tamam,
teşekkür ediyoruz.
teşekkür ederiz.
Biz de seni çalışkan bir öğrenci olarak tanıyoruz. Tekrar tebrik ediyorum.
Çok sağ olun hocam. Teşekkür ederim.
Tebrikler. Başarılar diliyoruz.
Şimdi kayıttan çıkmadan önce, şimdi kayıt kapanabilir Recep Hoca. Fehmi Hocam,
Efendim hocam.
bir özetler misin şimdi ne yapacaksınız bu belgelerle ilgili?
Hocam,
Arkadaşlar.
şimdi belgelerle alakalı Harun hocamdan o dışarıda olduğu için onun da fiziksel olarak yanımızda olmasını isterdik. Gönlümüz orunda ama böyle bir